everyone. We will continue today with our discussions of S-matrix theory. Remember, yesterday we discussed the toy model, which is where we thought about S-matrix as describing propagation of signals through space-time. This describes, and when we think of the S-matrix, and we know that propagation of signals through space-time should obey some basic properties like causality. And we use this toy model to get some intuition, in particular when we discuss the notion of analyticity, and then we saw how we got it to unitarity, and finally we discussed a little bit how to, very briefly, how it is connected to the actual relativistic scattering. And we saw that, okay, either it is directly connected if we discuss coherent states, but if we want to discuss the 2-to-2 scattering amplitude, there are some subtleties, and today we will continue, and the focus of the course will be on the 2-to-2 scattering amplitude, and this is a really essential object for the study. So in fact, I will consider 2-to-2 scattering of scalar particles. Remember that particles are labeled by their form momentum. So I will use say the mostly plus signature. So and have one shell condition. They're labeled by their mass, by their spatial momentum. So the energy is positive. And also they're labeled by their spin, or more precisely by some representation of what's known as a little group. But for my talk, they will not carry any spin. So they will be scalar particles, and we will simply label them by mass and spatial momentum. And when we talk about scattering, we think of state being described by state of free particles in the far past and the far future. This is not obvious, and in fact, in some sense, this is not always correct. It's a dynamical question. It's a statement that we have a Hamiltonian evolution, and when the particles separated from each other, say the Hamiltonian becomes free effectively, and we can describe it like that. And so if we talk about such theories, and I'm here talking about such theories, say, ignoring some subtleties like infrared divergences, then we want to, it's a quantum mechanical system, so we want to describe a Hilbert space. And this is the usual Hawk space. So it's described, we can describe it by annihilation and creation operators. So we take and the annihilation operators, vacuum. That I assume, of course, when I say the system as a relativistic, that it's Poincare invariant. Finally, then we can describe one particle state. In the vacuum. The scalar product in this Hilbert space. Measure is this invariant measure, and one here refers to one particle. finally, yes, where I define the states as the important formulas. These are all boring formulas. I shouldn't have, but the important formula is that we want to describe the Hilbert space of the theory, and it's given by a sum, direct sum over multi-particle states. With some multi-particle states. Of course, we want if we consider some superposition, we want the norm less than infinity, where the norm is some over norms in n-particle centers. And so this effectively tells us that we can write a formula which we use often, which is a resolution of the identity. It already appeared yesterday. Bonus lecture, so we have vacuum plus over all states. And again, the measure simply have identical particles, and let me, for simplicity, consider scattering of identical scalars. We have this 1 over factorial permutation symmetry, and you have again this. So let me make one. You see that the scattering, the identity operator here involves all kinds of multi-particle scattering. However, in practice, when people consider, say, for many years, the non-perturbative properties of amplitudes, and in fact, we have some understanding of 2 to 2 scattering, but all the other ones, 2 to 3, 2 to n, 3 to 3, they're much worse understood because they're just too complicated. So the attitude we will be using is that we will focus on the scattering of 2 to 2 particles, and then all the rest will be considered very. We will not effectively consider any other case. Now let me describe the properties of the S-matrix. So this is the Hilbert space in which we will be working. Yes, and another comment which again is slightly subtle. I told you that the intuition is that that as particles get far away, they become big. So that's why we have this construction. And just important, obvious but important comment that the sum here goes over asymptotic states. Asymptotic states are stable particles, and this is not sum over quarks and gluons here. It's really sum over pions, electrons, particles which we believe are stable. Well, pions stable in QCD, but now in the standard model. Now, as we consider this,
Sasha, there is a comment
yeah.
By Simone suggesting that thinks there is something wrong in the formula for F, the final state.
Oh yeah. Sorry, it's a wrong formula. It's true. I'm sorry. Thank you. it should be FP, P dagger. Thank you. Now, yeah, one subtlety here is that as we take two particles and we make them collinear, then it doesn't sound like the argument that they're well separated is legit, because if they're parallel, to what extent they're separated. Nevertheless, in the normal treatment of the S-matrix, we say that this is the description of a Hilbert space. And personally, I don't know if there is how to rigorously prove, say, this is not a problem intuitively, because it's a measure zero kinematics. You don't expect to have any problem. And so that's why we consider this, even though the integral includes also collinear momentum. Now we introduce the S-matrix. Also, Simone already introduced it. So I try to be as fast as possible with all these kinematic things. So we consider the incoming state and the S-matrix. The outgoing state, which is and if it's a quantum mechanical theory, we want state. This is the station that regular one matrix is used. Now, usually what we consider as in this setting is we choose some say outgoing state, and we choose some particular incoming state. Overlaps. And this is described by momentum kernels. So this is the momentum of the incoming particles and outgoing particles. So you have, if you have some wave function in space, momentum. Now the first property which is believed to be general, in fact, again, something definitely we expect to be true in gap theories, but also in theories with massless particles. It is called space-time. It's called clustering, and it's a statement that if you have this S-matrix, you can write it the connected part plus permutations. In this case, and you take the connected S-matrices for all subsets of particles. So the intuition is that if you take a bunch of particles and you separate it into groups which are separated by large distance, then the scattering becomes independent. So if we do the experiment here in Geneva, we will not hear about scattering in some other part of the universe. We can describe it separately. And the important thing is that the disconnected S-matrices, they come with momentum conservation for the particular group of particles. So we have some, say, incoming momentum from 1 to m. I minus J. And one And this is, of course, because we have a Poincare invariant theory, so the total energy and momentum is conserved. So you can ask, okay, well, while the intuition is clear that if it separates particles in coordinate space in two sets of in two groups, then the scattering is independent and the momentum will be separately conserved. But I think there is another maybe nice way to think about it is that you can ask, okay, say, well, this is S matrix. What is the most general symmetries of S matrix? What is how much symmetries we can have such that the scattering is still non-trivial? And this is the subject of what's known as a Coleman-Mandual theorem, which says that in fact, if you have a scattering in higher dimensions, higher space-time dimensions, I mean higher than 2, then at most you can have Poincare invariance. You can maybe enlarge it by some internal symmetries, and on top you can enlarge it with some supersymmetry. And this is what you can have. And otherwise, you can have more symmetries, but then the theory becomes free. And what is the example of the symmetries? Let's say you have a free theory where particles do not scatter. So you have two wave packets. You scatter, they just go through. And the results of this process does not depend if you separate the wave packet or move the wave packets. And so these motions of wave packets in free theory, which does not affect the result because they do not interact, is related to what's known as higher spin symmetries. Now you see that, and the scattering, of course, in free theory is just a bunch of delta functions. The momenta of each particle is preserved. It's just free theory. It's simply described by this Hilbert space, which we described before, but it's not now asymptotic states, but it's really the whole dynamics is just free. Now here, when we consider separated groups of particles, it looks as if like there is an emergent symmetry, because indeed the scattering becomes independent, and you can move the groups of particles independently of each other, and they do not affect the symmetries. And so then this clustering is somehow, one way maybe to think about it is nicely, it describes this kind of emergent symmetry. When particles are separated, you can move with packets, it does not affect the scattering. And these delta functions, similar to the delta function in free theory, where instead of just one free particle, you have these groups now, but otherwise the product is just described by a bunch of delta functions. Okay, this was probably very confusing, but I will just leave it as it is. It's not so important. If it was just all incomprehensible mumbling, just ignore it.
Sasha, there is a question by Tim Höne. What exactly is the product the pi you're summing over, these products there?
Oh yes, so these are the permutation of the particles. So you can take yes. So the idea is we take, say, n particles and we split it into all possible subgroups of, say, m and n particles, and then we sum over permutations among. So let's say we split it into several groups, and then each particle could be in every group. So you start with, say, well, let me now do the simplest and the most relevant example, and you will see. But the intuition is that the idea is that you take S matrix, you split into all possible subgroups of particles, and each particle can be in every subgroup. And then by the simple reason that you can separate subgroups in space-time, and they will scatter independently at the level of this operator. S operator is a function of momentum. It manifests through this property of factorizing on parts which have these delta functions for subgroups. Let me be very concrete with now a 2-to-2 scattering, which is the subject of our talk. But this is supposed to be true very generally and non-perturbatively, this clustering property. So let's take the simplest example.
Sorry, Sasha, I also have a question.
Yeah.
You mentioned that these higher spin symmetries that reduce the S matrix to the sum of many delta functions, right? And then if I understood correctly, you're saying that this clustering
Yeah.
is somehow in between.
It feels a little bit like this. It's when I separate two particles, there is sort of an emergent symmetry, right?
Yeah.
The scattering becomes independent.
But can you think of, is there a symmetry associated with this clustering thing, or only the full higher spin symmetry? You mean you identified as emergent symmetry?
It seems to me that there is effectively this effectively as a symmetry at large separation, so it's broken.
Okay.
So and the fact that it's weakly broken or
You're saying that
it manifests.
I see. You say that the fact that the clusters are an explicit breaking of the symmetry, but still it preserves.
Yeah, the scattering with each cluster is but somehow. Yeah, it looks like it's just natural from this point of view. If you look at the free field theory, it's a bunch of delta functions, and the clustering, which reflects on this again, the similar symmetry is also encoded in terms of this delta functions. But it's saying the same, that in each cluster the momentum is conserved. So there is one exact S-matrix, which maybe there's a. First, let me write a few formulas which are exact. First, when we say particles are stable, to take the connected it's 0, so it does not decay. If you start with one particle, it stays one particle. And finally, the connected element of one particle going to one particle is just one particle propagating through space-time. It's completely fixed. So the result is just this. Now let's consider the main object of our study. We take, say, 2 to 2 scattering. And we can take two particles and, of course, separate them this time. And this will correspond to this number of m and n being 1. So we have this S11 connected, say, P3, 1, S11 connected P4, P2, and then the sum of the permutation is simply we can now have the transitions from one to one. These are the fixed. These are completely fixed. This we already know. And this is the only known exact S-matrix in high dimensions because it's an S-matrix of a free theory. Now the interesting part comes from the interactions. And this is this S22 connected. And S22 connected is described by, I will write this I, momentum preserving delta function. And the central object of our study in red, it's this T function of Mandelstam S and T, which are energy and angle. So let me now write what these things are. So, sorry if you've seen it already many times. The Mandelstam S corresponds to total energy, the scattering, sum of 1 and 2, And then if you go to the center of mass frame, total energy, that's 4. Now T, which I define describes the angle. So here the particles is momentum k. They have scattering to the same momentum k, but now with the scattering angle theta, which is here. And finally u. And that is equal to it's equal to 2 squared minus theta minus 1. Now, in terms of Mandelstam invariance, the angle so the basic idea is, and this is of course nothing but total energy squared. Here, if I have this particle, each of them carry the energy E naught, which is square root of this. So when we sum that, 2 E naught, and if you take the square, yeah, so then therefore you see that this function T is a function of energy and angle. And then what we want to understand is to study its properties. Also, I said technical comment, I said that it's a function. And you see, strictly speaking, this sort of delta functions that appear here as the distributions. And strictly speaking, this function, we should think of this T as a distribution. And by this, I mean that it's a functional, which you can pair with function and it spits out the numbers. But in practice, when we do the computations, very often we treat this T as a function, and I will also do that. But in principle, if you want to be very rigorous, you might worry about that. Now, what is this? What is this function? Okay, another little comment just to have in mind that if you go through the dimensional analysis, you will find that the dimension of this guy is the mass, or something to have in mind. And when we write this T function, because in 4 dimensions, it's dimensionless. Now, let me discuss what is known as Mandelstam plane. So when we talk about S-matrix, we talk about scattering in various channels. So what does it mean? It means that, in principle, if you look at the way I define S, T, and U, there are several possibilities. So first of all, you can consider what I just erased, which is known as S channel. This is what it describes scattering of particle 1, 2, 4. And because the total energy, which is stored here, cannot be less than 4m squared, please describe the region S larger than 4m squared. And you can check that the formula is just erased, the T is this. Then there is T channel. Process 1, 3, 4, and this is the region Finally, there is a U channel for the same reason. That's one. Now, this is U. Now, remember that this three variables, they satisfy. This is simply if you use momentum conservation and you plug it in these definitions. And this is often depicted on the what is known as the Mandual plane. So you can take three vectors which have all separation 2π/3 between them, and then you can check that if you now plot points here like this. And you can check if this original point and all this axis are separated by angle 2π/3, so they're all equal. Then if you take a random point and you check what is t, what it's s, and what it's u, just by construction, it will satisfy this identity if you put here 4, 0, 4 squared, 0, 4 squared, 0, squared. So let me erase this. And so in this plane where you draw it like that, is known as the Mandual plane. And then the conditions that we describe for the different channels are like this. So here we go s larger than 4 squared. And you see that t is negative. So this is the physical region which corresponds to S channel. This is the region corresponds to channel. This is the region corresponds to the sort of starting point of the S-matrix theory and the important fact is that we will consider, and there was a question already yesterday, that we will consider this function t s of t. Originally, when we do the experiment, you see that both s and t, this is energy, this is the angle, or if we consider the scattering in the S channel, so if we do experiment, both S and T are real. However, the starting point of the S-matrix theory is understanding that in fact this function where S and T are real, it's naturally can be promoted to an analytic function, and in fact we should think of S and T as eventually as complex variables. Particularly, remember in the signal model, this was exactly the same. We had some energy, and remember that we could continue it in a, say, upper half plane due to causality. It's the same thing here. In fact, we will have some analytic function from which the physical amplitude can be obtained by landing on the real axis from the upper half plane. And then as soon as a priori, when we started with this function of real variables, it's that is the end of the story. But then, as we realized that it's an analytic function, there are many questions that arise. What is the analyticity domain? what are the properties, analytic properties, a function of two variables, etc., etc. And this is, in a sense, one of the central questions of the S-matrix. We will discuss it more, but just to give you an example, for a priori, let's say you measured this function in some range of energies and angles, and then let's say you manage to find this analytic function, which produces this actual physical experiment data. And then you might ask, okay, well, let's say we did the experiment in S channel and we find this function of S and T. What happens if we just take this function which we found and we analytically continue S and T in such a way that we land in this region? So a priori, if you're very naive, you find the function which describes the scattering in the S channel, and after you analytically continued, it has nothing to do with scattering in T channel and U channel. You could have thought, I mean, it's a complex plane. But the miracle, so one of the many miracles, is that in fact, what you will find that the same function will, after you analytically continue, will describe all these three channels. So in fact, all these three a priori, for the experimentalist a priori disconnected regions, they will become a part of one single function, which describes all of them, and say these properties that you can get from here to here by analytic continuation, by say going to the upper half plane, is known as a crossing symmetry. But for now, I simply say that we will have this function and we would like to understand its properties. So now, just give me a second.
This Mindless plane, is it? It's useful to visualize the kinematics, but it's also useful to think in the context of this analytic continuation.
It is, yeah, it is sometimes useful. For example, there is this. There are various properties which are interesting. So, for example, one fact, at least for scattering of identical particles, is that inside this triangle, so this triangle here is S, T, U between 4 and squared and 0. You see this triangle does not correspond to anything physical, but you can show, or it is known fact, that the amplitude is real inside this triangle. Then when you do the crossing, say if you want to go, you want to do the crossing transformation, say there is a story of Ross-Epstein and Glaser path, and you can show that, for example, the Ross-Epstein-Glaser path, something like this. But this I will need to explain. So it's just, it's not crucial, I mean, it's kinematics, so it's probably not necessary, but I just wanted to describe it because it's some standard thing. And then as we will understand later, even though we start in these regions, which are physical regions, S, T, and U channel scattering, then in fact we will be interested in a whole Mindless plane. You can discuss what happens when S and T are both positive. It is not described immediately by some physical process, but in fact we will see that it has some physical interpretation, and we will discuss it. So, even though just what we measure in the experiment is normal in these three regions. Now, let me start describing various properties of T, and well, the more complicated questions that we will discuss next is what is its analytic properties as a function of two complex variables. But for now, let me describe something simpler, which is unitarity. Maybe before that, as there are some questions about this very basic kinematics, I apologize for this maybe a little bit dry part.
By the way, we turned on the microphone, so we habilitated that you can speak. So if you want, you can just unmute and ask your question now. Also, during the talk, you can raise your hand, but then you can also speak, and so that you can interact directly with Sasha.
Okay, very good. So as again, Simone wrote yesterday, what we just discussed, we can write sometimes as 1 plus t, where 1 refers to the disconnected part of 1 to 1, and t is this part which describes 2 to 2 scattering. And now we can consider the unitarity relation, and remember, unitarity relation was that as Zegger was to 1, now if you plug this structure of 1 describing the disconnected part, 1 to 1 transition, and t connected part, we get this this relation that that has already appeared yesterday. Let me write it again. 4 t minus just to be very precise. Again, to connect to what I wrote on the previous blackboard, this matrix, this operator T is by definition inserted states. It's it gives you this delta function, momentum conservation, times the function T of S and T that we care about. So yes, by inserting this identity here, 1 cancels, and we're left with this T minus T dagger. And here we can sum over all the states. So here I use this completeness relations that we introduced at the beginning of the lecture. And here we have a set of momenta. Again, when I'm writing this relation, I use the fact, all these little kinematical facts that I already introduced, is that the stability of 1 particles implies the transitions from 1 to 2 are 0. Therefore, the sum starts from 2 and goes to infinity. And yes, here we use the completeness relation. Now, note that something obvious, but if you have this n particle states, there is a minimum energies that you need to produce them because they have mass. And say if you take this energy S, this n particle contribution starts for S larger equals n squared. This is the total energy, if you remember. S is the total energy square, and you can only produce n particles. So this unitarity relation, it has this hierarchical structure where when you increase energy, you can produce more and more particles, and so more and more terms appear in this sum. Now, let me now massage a little bit the left-hand side. You see that on the left-hand side, we have this as T dagger, and let's get rid of it. So, well, let's take this part, 3, 4, T dagger to 1. This is Hermitian conjugate operator. So same as conjugate. And for identical particles, if P3 and P4 are identical to the P1 and P2, there is a Lorentz transformation which maps P1, P2 to P3, P4. So in fact, this matrix element is the same as and this is only true for identical particles. So then you get, we get on the left-hand side, this is also appeared in Simone's first lecture, we get T of S and T minus T dagger of S and T, which was the imaginary one. In fact, because recall that this is nothing else. Now, in fact, something else is true also, which allows you to get rid of this star here. And in fact, it's something which also allows you to avoid the step of talking to identical particles. And this is a property known as the Hermitian Analyticity, which says the following thing. Says this function T let me elaborate a little bit on that. So remember, first of all, we described our physical amplitude in the I epsilon description. So it was 0. So therefore, when we talk about some physical scattering, we can imagine that we take S to be slightly in the upper half plane and then take the limit. Now, the statement here is that if you take this T slightly above the real axis, and so we just looked here and said that this matrix, which involves T dagger, is T star. The statement of Hermitian analyticity is that instead of taking this complex conjugate, you can go back to the original function and just take the conjugate S star, which is to take S to the F minus I epsilon. Physically, what happens is that if you consider the scattering amplitudes, and again, if you did the exercise with the bubble, saw it, that there is a cut in a physical plane. And so let's say it starts at 4m squared, and the physical amplitude tells you that you should land it from above. This is what T is. And Hermitian analyticity tells you that instead of taking T star of the physical amplitude, you can equally go here to this S from below. Now, this is something, this property of Hermitian analyticity is something which is true in definitely in perturbation theory. You can also prove it in quantum field theory or in S-matrix theory, but I will not go into the proof. Intuitively, what it means is that if you have a function which is, say, real along some interval, and you want to, you can define its analytic continuation. So let's say you have a function analytic in upper half plane and real along some axis. You can define its analytic continuation to the lower half plane through this equation. So you see the point now. What I was trying to do here and what he tried to achieve is that now the left-hand side we start with t minus t dagger, and now I said that t dagger is something which is the same as amplitude but going down out below the cut, and therefore what we get on the left-hand side is 1 over I, say here t s plus I epsilon t minus t s minus t, and this is something known as the discontinuity of the amplitude along the say certain cut. So we see that in the unitarity relation, the left side you get the discontinuity, and the second comment is that if your particles are not identical, then you cannot do this step. So you cannot do this step, and then you would say, okay, well, then you cannot write something here as t minus t star, but this step you can still write. So this matrix element for non-identical particles will be related to the original function going below the cut. So in fact, the structure of unitarity as a statement about the discontinuity is general, and it applies for non-identical particles as well. So just take this. This definition, and now what do we get in the right hand side? And so this, in my notation, this discontinuity, so the difference of going above and below, I call it and divided by I denote it by TS. This subscript S means that we take discontinuity in the S channel going above, going below, taking the difference, and taking the difference dividing by I. Okay, so this is the left-hand side of unitarity equations. So this is the general story. When we will look at unitarity, it relates cuts of the amplitude to, say, in the right-hand side squares of the amplitude. And now let's, for simplicity, we can consider first the elastic. So I told you again that it was the unitarity equation was such that if you restrict the energy below certain region, no other particles appear. So let me first take the simplest possible situation and take S between say 9n squared, 4n squared. So this is the energy energy which is enough to produce two particles, but not enough to produce more particles. And so this in this region, the only term that contributes here is n equals 2, and this is known as elastic unitarity. So, and you can work out, and it's done in the notes, that what happens here is that, well, you just get this relation, say Ts of S and T equal some factors that you can work out. And you integrate over angles, comes from g mu 2 in this integral. And here you have some known kernel. Where I introduced z is just a cosine theta. So it's a scattering angle. And here you have the amplitude plus and yeah, so here the only information is that we see a quadratic equation, so you can work out the kernel. It's known. This t is a function of z. It's just a relation between Mandelstam t and the cosine angle that I wrote before when we introducing the kinematics. And again, just
Sasha, Santiago Agui asks, what is in the denominator of the formula for Ts? I'll read this.
Sorry, it's just kinematical factors. So let me make a few comments about this formula. So first of all, you see that when the theory is gapped, you have this hierarchical structure, and you have this formula. When the theory is not gapped, all this is lost, and you cannot study this simple equation because when m is 0, all the amplitudes come at the same time. That's one big difference between gapped and gapless theories from the point of view of this unitarity equation. Second, so this T and T star arose from T dagger and T. And here, as I just explained, is what we call T is approaching S from above. Sometimes it can denote it as a plus. And T star by Hermitian Analyticity is the same as approaching S from below. So this is T minus. It's again, just to emphasize that this is an equation for this function T. We just have one function of this complex variable, and we study its behavior in the complex plane. And what this equation tells you that you take the discontinuity of this function, and then it's equal to the square of the same function. One is taken above, one is taken below the top. The second comment is that, again, in the exercise, if you did it, if you take a Feynman graph, let's say you have a theory, something like 5 to the 4. And this is just amplitude lambda. Now, let's say you take square of this guy. This is a slight generalization of the example with heavy particle. So again, you can check. Let's take this is a lambda square, right? This is lambda lambda. You can compute this bubble and take as discontinuity on one hand. This will compute the left hand side. And this on the right hand side, you will, if you plug the 3-level amplitudes and you do the integral, you will get the identity. Now you see, this is what Feynman diagrams do. If you compute the Feynman diagrams, no matter how many, you will always find that order by order in lambda, all this is satisfied. However, you see that to satisfy this equation, the leading order, which is lambda squared, you have to take t to get this plus this. Now, this is the first term that contributes to the left-hand side, and this is what satisfies it on the right. However, if we added the contribution lambda squared to t, therefore we will get on the right-hand side now new contribution lambda squared times lambda, which is lambda cubed, which should be canceled by something here, which is that you have to add an extra term, which is this. So you take two bubbles. Now this will be lambda cubed, etc., etc. So you see that order by order in lambda, this equation is satisfied by Feynman graphs, but this equation is a non-perturbative equation. So this is a, you can ask, okay, so what do we have to add to the series, or how do we define it non-perturbatively, so that this equation is satisfied? And this, I think, is a very interesting question. How do you say, you know that Feynman graphs produce you the perturbative solution to this equation? What are the non-perturbative solutions to this equation? And this is something that has been studied. I will maybe not go into that, but this is maybe the simplest example where there is this, you can ask this question, what is a non-perturbative scattering amplitude? And we see that by its nature, non-perturbative scattering amplitude is the solution to this equation. And then we do it by Feynman graphs, but we would like to understand what do we need to add to Feynman graphs to make it a full non-perturbative solution. For example, one interesting thing that people tried, and it sometimes works, is that you can think of this equation as a iteration map. I mean, this is closely related to Feynman graphs. You say, okay, well, I start with this, I plug it in the right-hand side, I find TS, and then effectively you can imagine that you can reconstruct from the imaginary part the full amplitude, and then you can try to start the iterations. And this is closely related to Feynman graphs, but this is a non-perturbative in principle procedure. And then there are some theorems, mathematical theorems, when this iteration procedure converges, and it would be very interesting to understand what exactly do we have to add to Feynman series, to this perturbation theories, to make it non-perturbatively well-defined. So what is the extra ingredient to go from the series to the solutions of these equations? Because more generally, we understand by now the perturbative S-matrix theory is a solved problem in a sense. We can just compute Feynman graphs. Of course, it can be very complicated, but what do we need to add to this amazingly developed and recently revolutionized understanding of perturbative amplitudes to turn into a non-perturbative gadget? I think this is an open question. So this is the simplest, beautiful equations in the S-matrix theory. But let's go further. So,
Sasha, do you want to take a break now?
Oh, yes, I completely forgot. Yes, let's take a break.
Okay, let's have a 10-minute break. And if you have questions during the break, just speak aloud, and probably will resonate here in the room. We can hear you and discuss it. Okay, see you in 10 minutes.
What does PD of set Z1 and Z2 stand for?
Stands for? What's the question? What is it stands for?
Yeah.
Yeah, it stands for the following thing. So remember how we got to this equation? We take this formula. So now take mu2, plug there the explicit definition in terms of two-particle phase space integral, and then massage it. Do the integrations, and you'll find that some kernel. So going from here to here, it's a kinematical kernel. It's a kinematical kernel it's explicitly known. And if you look into the notes, it's given by equation 53. I put the notes on Slack. I hope you can find them. And so it's a little bit messy formula, so I didn't write it, but you can find its explicit form in equation 53. It's a kind of interesting object mathematically. It's, for example, I think it's given by a product. It's given by a sum of all spins of the product of the Jandar polynomials at points z, z, z prime, and z double prime. But it's a known function.
Okay, thank you very much.
Question two, actually. How do you, from the signal model that you presented last week to here, is it obvious that
It was yesterday, not last week.
Yeah.
You are living an intense life.
I had such a bad night.
Yeah.
It seemed like weeks.
Sorry. Yeah.
No, is it obvious that here, because here you're assuming T is real, right?
So far, yes.
So is it obvious that T should be real, or because T you can write it as energy times cosine?
Yeah.
So yeah, I was wondering whether from the signal model to taking T real is obvious, or it could be complex.
In fact, signal model does depend. It is related to real T,
Okay.
but it's related. So in the physical region. So I described this Mandual star triangle, and remember, it's got three regions as positive and T negative. You can ask, for example, what if I take S positive and T no, also positive? What is it? And this is sometimes called unphysical, but in fact it is physical. It describes a scattering where instead of preparing particles in momentum eigenstates, we separate them in an impact parameter space. So they separate at some distance b. And so this is related to the integral over dq e to the I q s, where we set t minus q squared. And then what happens, so q is here a real vector, so indeed t is negative. But what happens is that as you take this integral, effectively what you can do is you can deform it, and it's controlled by the singularity, nearest singularity in t-plane. For example, you can imagine that you have a massive pole, massive exchange. This is just a propagator. T minus m squared, right? Mm-hmm. You see that this has a pole at q equal I mu, Im, and this pole gives a Yukawa potential. It gives e to the minus Em. But if we set q to be complex and Im, it's T positive. So in fact, the positive T describes scattering in the impact parameter space, and the nearest singularity T describes the size of the object. And when I talk about signal model, I was considering this picture of two wave packets separated, and so this is related. More like, okay, thanks. Nice.
Sorry, can I ask you?
Yeah.
Before you were talking about higher spins,
yeah.
But I mean, in general, if I write down like a Lagrangian with higher spins and coupling and so on, how do I see then that the S-matrix kind of like factorizes?
Well, first you will not be able to write if you try to write interaction, let's say we I don't know which particle you would like. Let's say we take a particle spin 5. And let's say you say that is self-interacting. Then you will see that you cannot do that, because if you have spin 5, spin 5, spin 5, spin 5. Well, first of all, if you want to do Lagrangian, you want it to be weakly coupled, right? Because if it's strongly coupled, Lagrangian is. So let's say you have this diagram. Well, let's consider the signal model experiment. And then what you will find that your S will be 1 plus I C, well, this is lambda, squared. And here you will find omega j minus 1. So remember, we concluded last lecture that j is less or equals than 2. So you'll find that it violates causality.
But here you have a 3-point vertex, right? Yeah. If you have a contact interaction between the 4, it's okay, no?
Okay, let's do that. So this you cannot do. Well, first of all, physically this will be in trouble, because you always have this, right? With the graviton, because everything gravitates. Yeah. And then you will be in trouble, because now you can consider something like this. Let's rotate that. Yeah. Two, 5. And this will be trouble. This will lead to the same exchange, particle exchange, which allows you to send signals, even though you change your identity, but it's fine. So, okay, but let's say we don't want to do gravity, we just want to do the spin 5 S-matrix. And you say that the leading amplitude of, say, spin 5 guys is just some kind of matrix like this. I think this will be also trouble, because this, I mean, you can consider scattering at 0 impact parameters, and it will also violate causality. So, okay, then you'll have to add all of them, but then, okay, how do you add all of them? Yeah. In other words, whenever you try to do that, you somehow either have to do it strongly coupled, or you have to add all spins. So the usual lore, I guess, that if you want, in fact, let's say you want to make a vector particle massive, then you add Higgs. Let's say you want to add higher spin particles, then you have to add string. So string is a kind of a Higgs for higher spin. It's a mechanism to have higher spin particles, because having a string, and by string I don't mean a fundamental string, could be QCD string. What you find is that QCD flux creates all these glue balls, and they all consistent, they do not violate causality or a fundamental string. But it's always, I think it's fair to say that all known theories, higher spin particles, they are this type. So if you add one, you have to add all of them. Effectively, why it is the case is that because you see one of them violates it, but okay, why don't we do something like this? Sum over j, and then it goes to the denominator, and then you're fine.
But I have a question, because this argument was perturbative in the lambda, right?
Yeah, yes, this is perturbative. Yeah. If it's strongly coupled, then you have to just, reduce the S-matrix.
In that sense, the gravity can somehow be taught separately, right? This is what you're doing.
Yeah. So
so string theory is still fine because it adds all the students.
This break was much more useful than the whole first lecture. So.
Yeah, we now put them that they can come in themselves.
Right, it's good.
Try to perhaps interact. Yes, you can start whenever you-
Can I start?
Yeah.
Okay. So I just remembered another curiosity which I wanted to tell you about this equation, because it has an interesting history also in which is the following. Let's say we're doing a collider experiment. So we consider scattering of particles, and we consider them scattering at low energies. And what we do in collider experiments usually is that, let's say we have this function t of s and t, and then we measure its absolute value square, which is a probability, which is known as a differential cross section. But you see that this function t, okay, well, let's say we measure its differential cross section. So let's say we measure its absolute value. What about the phase? What can we say about the phase? Well, measuring this phase is very complicated. In fact, I don't know. Maybe Simone knows if there is a good way, direct way to measure such phases. And sometimes it's easy if you have a resonance, you have a direct relation. But in general, these phases, in general, phases of amplitudes are related to the really quantum mechanical phases. In fact, the overall phase of an amplitude of the S-matrix is not observable. What is observable is the relative phases of the S-matrix. So, but here you can ask, is it true that given the absolute value, we can plug it in this equation? You see, this equation will become equation for the phase. Because, well, it will depend on absolute value and will depend on the phase. And the question is the following: given for the collider experiments, given differential cross section is uniquely fixed. And this is the equation. The question about this equation, given differential equation, is the solution of this equation unique? And for with some extra condition on this phase, that let's say it's not too big, people have proven that the answer is yes, it is uniquely fixed. But overall, to prove it in a complete generality is still an open, interesting problem, which is try to show that the solution to this equation is unique given a differential cross-section. So this is just a curiosity. Now, let's go to S larger than 9n squared. Well, if you look at the unitarity as it was written with this n particle phase spaces, this is complicated. This becomes complicated very quickly. You don't want to talk about n particle phase spaces, etc. So it is not very useful in this form, unitarity. So instead, what you want to do is that, and this is related to the known as a partial wave expansion. You want to resolve the identity, the space, the complete set of states, which we have in a theory, not in terms of the multi-particle states, but in states which carry some center of mass energy and angular momentum, and maybe some projection of the angular momentum on some axis. So, of course, if we have some multi-particle state, we can construct such states. So let's say we take a two-particle state. So there's an overlap. This is given by this. The energy of this guy, and then you have explicit spherical harmonics, which are known. And what happens is that because the scattering is Poincare invariant, in particular it is rotationally invariant and translationally invariant, this basis of states, as opposed to these ones, which do not carry definite momentum, but the momentum is conserved by a scattering matrix. If you prepare a state with momentum J, then after scattering, the angular momentum will not change. So this is a nicer basis in which you can diagonalize the scattering, and then you can define the partial waves as effectively that's what they describe, the function of this total energy squared and the spin. And they're given, they're proportional to the matrix elements this T matrix in this basis. Because the scattering is rotational invariant, so because this T does not have any preferred direction. In fact, these matrix elements, they do not depend on this projection of M. And you know probably this already better. I thought that this is, I guess, known in quantum mechanics as Wigner-Eckert theorem, the fact that this does not depend on M. But just again, we are going to the partial waves, which are really the meaning is simply we evaluating this T in the states of two particles, which we prepared with a given angular momentum. And then we can take our matrix TST and expand it in this basis, and we find that we get the sum over spins all the way to infinity. There is some normalization factor. It's in the notes. I will not write it. It just depends. It's an explicit function, partial waves, and PJD plus theta. And these are effectively d-dimensional Legendre polynomials, which are related to this y's in a simple way. We can go through the unitarity equations as we wrote them and switch everywhere to this basis, and then we will arrive at this formula where now we have this F's sandwiches between Pj. So this again explicitly written in the notes. These are just some polynomials. In 4 dimensions, these are Legendre polynomials. In d dimensions, these are proportional to Eigenbauer polynomials. This is also a function, and so all the information is here. Now, what happens is that if we switch to this basis, all this mess with multi-particle states simplifies because, and we can write a neat unitarity relations in terms of this partial waves. So, how does it look? First of all, let me tell you what happens to this equation. So let's take now this equation and plug here this formula. In fact, what you will find, not surprisingly, that this this messy equation becomes simply the statement that the no, I can write it like, let me write it like this. So this is the same as the discontinuity of this thing. It's equal for this f of j's. It's equal to imaginary part. So the left-hand side becomes the imaginary part of f of j. And on the right-hand side, you have s minus form squared minus q over 2 square root of s. And you have s squared. So this is true. This equation, this is elastic unitarity. This is true here. Now, what happens as we go above production of next particles? Well, it's very easy. What happens is that in this equation, remember the new terms appear, the multi-particle terms, multi-particle. And the only effect of this multi-particle terms is that they, you can show that by the nature of the fact that we have T and T dagger, they can only contribute positively to this equation. And therefore, the equations that we get are the same, but instead of equality, we have something like this. Again, let me just emphasize that so what I'm doing is I'm massaging unitarity, a nice form where it becomes simpler. Another nice way to, so okay, you see that the difference here between left-hand side and the right-hand side is exactly the production of multi-particle states. So when there is no multi-particle states, they're equal. When the imaginary part is larger than the right-hand side, the rest is taken care of by the multi-particle states. Another nice way to rewrite this equation is the following. You can take define Sj of S, define it as follows. In fact, this one corresponds to the no scattering. And remember, when there is no interactions in a free theory, all this t is 0, f is 0, f equals 0, solve this equation trivially. And so SJS equals 1 is a solution to the unitarity. And so the unitarity is in, again, this equation just becomes SJFS equals to 1. This is elastic scattering, elastic region. And this equation becomes SJFS less or equal than 1. This is general. So this is a type of equations which are truly non-perturbative, and this is something which, when I was saying that when we were discussing the idea of combining what we know with basic principles, this is one of the very important ones. Because this is an expression of quantum mechanics, if you wish, that we have a unitary evolution, and we want to compute these things. Now, let me introduce yet another formula, which another way to solve this unitarity. And of course, you can say that one easy way to solve unitarity here, we write SJFS as some phase shift, delta JFS, and the unitarity simply says that either this is a pure phase, which in case imaginary part is 0, and more general condition, simply the statement that the phase shift, the imaginary part of the phase shift is non-negative, because you see, if it's a non-negative, then the S will be less or equals than 1. So this is the most general solution to unitarity. And in terms of the F, let me now plug this into this equation. We can write JFS equal okay, so you see that this, you might say at this point, okay, well, if this is a basic principles, then, okay, we just solved them. It's trivial. Why are we doing the S-matrix bootstrap then? Because let me just take this formula for T and just plug there bunch of S, JFS with some random phases which satisfy that. But as it's easy to see if you try that in this way you get functions which does not have some other properties. In particular, it will not have a crossing symmetry, will not obey crossing symmetry. And that's when I was telling you, sorry, we haven't discussed this crossing symmetry, but the point of when we discussed in the first lecture is that the main thing I was trying to say is that in relativistic theory, when we start combining basic principles, we get this rigidity of bootstrappiness, which is that we cannot simply do that. And in fact, that's example of this is that if you try to take say solution to unitarity and plug there, you will start violating other things which you want to satisfy. And then if you start obeying other things, you will start violating unitarity. And so it's in general or not. So in general, it's not that it's hard to satisfy one of these basic principles, but it's hard to satisfy all of them at the same time. That's where the interesting part comes from. But before we go into discussions with other properties, I want to how much time do I have? Do you know, guys? 20 to 12. When did I start? 10, I think 10. Okay. I will then finish with today with some few comments, which is, I think, are useful. So this has been a bit maybe abstract, but I think it's important. So please, I'm glad that I hope you have seen these formulas by now. One maybe a useful connection, which is related to physical intuition.
Sasha, can I ask a question about your comment before? So, with respect to the conformal bootstrap, for instance, okay, unitarity is also important, but besides crossing, there's also PE consistency. So crossing is expressed with some specific limits, and so sometimes even if unitarity is not there or positivity is not there, it's still constraining. So it's not easy to satisfy crossing by itself. Are there limits of this kind, like Regge limits, etc.? How constraining are there for the S-matrix? Can you satisfy crossing and all these limits with no unitarity? With no
so you just know unitarity.
Yeah, just no unitarity.
So
essentially, the question is if those limits add something useful or not in this case. Like,
so I guess if if I just start writing polynomials which are crossing symmetric, this is trivial. So this is a boring, of course, situation. Now you can say you do not want to have polynomials. You want to say maybe have cuts, but maybe no positivity on the cuts. Or you would like to have a function which have certain singularities and that decays in some way. Maybe then it becomes interesting. But somehow for the S-matrix bootstrap crossing by itself, I don't know. Yeah, it's an interesting question. I'm not sure, but it's clear that in fact unitarity is so strong here that the actual S-matrices is very important. And yeah, but by the way, one important thing is that also to emphasize. Remember, we started with the unitarity equation being S as dagger equals to 1. This equation should hold in all states. To reiterate, we simply consider this equation and evaluate it in the 2 particle states, and we solved it here. But we could have done it in the n particle states, and so it's much more complicated. I want to end today to connect a little bit to physics. Because at this point, you might look at these formulas and the sum of Legendre polynomials, some FGFS. What are we talking about? And for this, it's useful to use impact parameter representation. So what is the impact parameter? Impact parameter is the idea. You take your particles and you prepare them in a wave packet such that they carry some momentum, but in the transverse plane they're separated by some distance b. And then it's very intuitive because you take you take 2 particles. If you separate the wave packets, the interaction should decay. So this distance b, which separates the wave packets, is called impact parameter. Now, what's the relation of impact parameter in this formula? Recall we started with this thing. Under polynomials. And again, something which you might worry is that this picture, okay, it's nice, it's an intuitive, but it's a little bit imprecise. For example, what is this? So let's say this wave packets are low energy wave packets. Well, wave packets tend to spread. So what exactly, okay, we can maybe prepare them that when the region of the collision, they're separated by B, but then as they depart, they also interact. So this is an intuitive picture, but it's a bit vague, maybe. So, or maybe subtle, not because you have to worry about the dynamics of this wave packet. So instead, I will introduce it slightly differently. And I said, okay, let's just take this equation and consider the following limit. And I claim that whenever it makes sense, whenever this picture makes sense, this limit will reproduce this picture. So what you do is that you simply take the following limit. You take S to be large, so we consider it high energy wave packets. So we can really, this is a carry high, these guys carry high energy, but they do not have large transverse momentum. And I take J to be also large. And this is quite intuitive, because if you want to separate things in some distance, you do not want to consider some fixed J, because if J is fixed, it's a scattering of spherical waves, so they're not separated in any way. In fact, so if you want to separate things in distance, the relevant angular momentum is a large angular momentum. It's not a state with a. And so you take this limit and you keep B, which is defined as this, fixed. Now, you can see that this formula, if you plug here definitions of F, which is like this, and let me define the phase shift as B as the limit, take S to infinity, to take delta J equal this S. So I just go from J and S. So this thing depends on B and S, and you take S to be large and you take J to be large, and you take this limit, and the fact that this limit exists is related to the fact that this picture makes sense. But let me, at this point, I'm just postulating for you that this limit exists, and you get some phase shift as a function of S and B. Now, what you can check is that if you take this limit at the level of this formula, what you get is you can go from the sum over J to the integral over B. You can take the limit of these Legendre polynomials. And what you find is that this formula becomes that formula. And or alternatively, so this alternatively, you can define this this phase shift as let me find this now as a if you invert this formula, given by the and this is, of course, precisely what we mean by this picture, because what does it mean that two objects are separated by some distance? It means that if they exchange some momentum q, fixed momentum q, instead of fixed momentum, we go to fixed distance, so we do Fourier transform with respect to the relative momentum. So this is, if we consider now scattering Astroparticle, which exchange momentum q, and we say instead of momentum on to fixed distance, that's what we do. So here, instead of starting from this, in principle, I could have started from this picture with this formula. Here I derived it backwards. I started with the partial waves, and I define this limit, and I get to this formula. Now, from the derivation, it's clear that all these formulas, they have corrections, because I'm taking the S large and J large, keeping something fixed. So all the formulas, this formula is exact, but already this formula, there are dots, and there are corrections. And these are corrections either large S. So there are terms which are suppressed by 1 over S. And similarly here, so there are terms which are suppressed. Now, this object S of S and B, this is precisely the object we considered in the first lecture in the signal model. This is the S-matrix, which describes the scattering of two objects separated in B. And the unitarity, remember, unitarity was that Sj of S less than 1. If you take J to be large and S to be large, this equation holds still. So we get S of B less or equals to 1 for S large and positive. So, and remember in the first lecture, I said, okay, well, this was omega prime, and then we had to consider omega negative. But here you see, you can see, or we will see more, that this equation, everything was derived only for S positive, and if you try to take S to the negative, you are losing this condition. Now, I want to end with the most famous result of S-matrix theory, which I will derive in a slopy way, and then I will derive it in a rigorous way.
Sasha, sorry. The scaling would be fixed that you choose J with square root of S. Is it justified only by the end? So you got what you wanted. So that was the scale, or is there a reason why J needs to go?
I think there is an intuitive reason. So let's say we consider, yes, it should be something very simple. So how do we?
Are you referring to the fact that this case like square root of S? Isn't this just dimensional analysis?
Well, that's I think it's a cheating answer. So I don't want to give a cheating answer.
J is dimensional S. So square root of S is fine.
Yeah. So, but you're asking, I can write here a function of square root, but since I take S to be large, we need just to take a leading asymptotic.
Right.
And then the leading asymptotic, the question is the angular momentum is linear with energy here. It's okay. Should be able to answer, but that's homework for me. So let me end with the Poisson bound derived in a slopy way, and probably the most famous result of S-matrix theory up to date is deriving it rigorously. But this requires some work. So what is a Poisson bound? Bound on the total cross section, and the total cross section is effectively defined bound on total cross section at large energies. It will be effectively defined here by 1 over S imaginary part. We're considering a scattering, forward scattering, and the angle is 0, and we take the discontinuity or imaginary part with respect to S here, and we ask how it behaves as a function of S. Now, if you take this formula that I wrote there on top, T as a function of S and minus Q square, setting t to 0 is the same as setting q to 0. And take an imaginary part. Well, it's taking an imaginary part. So we will get that this scales up to some irrelevant constant. It gives g to infinity to b d. And here we get the real part 1 minus s. Yeah, what I did, I just defined a new quantity, which is the total cross sections, could be proton total cross section, whatever, pi and pi. And then we take this formula above and we set q to 0. Intuitively, it just describes the integral over all impact parameters with some weight. And remember, this s, the absolute value, is less than 1. And now the question is what happens at what happens to this integral? Well, what we expect is that as we integrate over b, this interaction eventually is turned off. Let's say we fix s and we increase b. Well, as we fix s and we increase b, we have the picture with two-wave packets. Eventually, the interaction between becomes small, and s goes to 1. Right? Because I told you s equal 1 with no interaction. S goes to 1, so this integral is cut off at some scale. And this defines for you a total cross section. Now, how quickly it goes to 1? Well, how quickly it goes to 1 depends on what is your force mediator. For example, if your particles exchange.
Sasha, there is a question from
Yes.
Sergio Ricosta. Remember that you can unmute if you want. Your new formula is S of and b, or 1 minus s.
Here it's 1 minus s.
Above one where you define s of s and b. Can
Sorry?
you hear me?
Yeah, we can hear you.
Yeah.
I'm confused because
Yes.
maybe I'm not seeing.
You're right.
Ah, yes.
Yeah. Thank you. What's wrong? Yeah. Very good.
Thanks.
So, well, one part of this question is easy. So, and that's honest. Let's say we have some scattering of particles, and let's say the lowest state we can exchange is, for example, 2 pions. Then as we go to the large distances, and I guess the reason here is that I'm talking about this, if I consider scattering of pions are pseudoscalars, and so the lowest state you can exchange here, go back to pion is a pair of pions. Then, as we go to large distances, well, we have a Yukawa potential. And Yukawa potential means we have just a mass of a state times b. So here, if the mass is 2m pi, this part is easy. As we fix s, as we increase b, eventually s decays exponentially. This is just a statement that the theories get. However, the question is, and this is where the derivation becomes shady, how does this object depend on s? And it happens at this point. At this point, from everything I told you, we don't know. But that's where it will be. But a natural thing to expect is that this delta, the phase shift, okay, we exchange the particles, but here, this phase shift depends at most, it grows with some power, s to the n. Now, why is that? Well, it's already pretty generous, and it is expected, it is true for if we exchange some particle or some spins, if we exchange the state, this is also reasonable. But it's not completely clear when exactly this formula kicks in, what is this power of n, but let's assume that the interaction is such that these particles, the function of energies, they decay like a polynomial, and as a function of b, they depend on mb like that. And again, from this signal model, we do not expect n to be larger than 2, because when the phase shift becomes small, we do not expect that this guy. It's exactly, again, we're back to the signal model. We do not. In fact, for the phase shift, it was not larger than 1. Remember, s was prime, and we showed that this in the previous lecture. We argued that this should be less or equal than 1. So this is the expectation, but let's assume that even more generously that is like that. Then you see what happens is that this integral effectively is cut off when this object becomes of order 1. And this object becomes of order 1 when, well, you can plug s with this formula into this integral and evaluate it, but you see what happens is that it effectively cuts off the integral at b star, which is when this guy is equal to 1. And this b star is n over 2 and pi times log s naught. So it just scales logarithmically with s. So therefore, you see that effectively what we have is that this integral is bounded by some constant, like here we put b star, b minus 3. So here I use the fact that this object is bounded by 1 by unitarity. So at long impact parameters, this is bounded by 2. And at large impact parameter, it gets killed by the Yukawa potential. So we get this integral, and this is b star minus 2, and this is p log s is naught. So this bound in the total cross section that it does not grow faster than log s to the d minus 2. The most famous is when d equals 4 in 4 dimensions, log s squared. This is known as a Froissart bound. And physically, it comes from two things. I hope first it comes from non-perturbative unitarity, that this guy is bounded by 1. And second, at large impact parameters, because of the gap, you expect the phase shift to be of this type. And just these two very general facts, unitarity is obviously true always. This is also always true in the gap theories. Eventually, we can prove it. You will get the bound, this bound. Now, in fact, there are various floating C's, constants, S naughts here, but you can make it completely rigorous, completely precise, and I will do that. But the basic picture is that. I guess for interesting comment also, you can ask: is the Froissart bound saturated at LHC? And or when do we expect the Froissart bound to be saturated? Or I don't know the answer to this question, and I don't know to what extent we understand it in QCD. The current experimental data is more consistent, my understanding, not with Froissart bound, but with the growth of this type, S1.08. So for the amplitude, note that if we divide it by S, this gives something which violates Froissart bound. I think this is known, this behavior, which is known as Doniczy-Lanczos-Pomeroy. There is a famous paper. Doniczy, I don't know how to say it correctly, his name, but anyhow, this current behavior violates the Froissart bound. But I think there is no reason to expect that at the current energies at the LHC, the Froissart bound should be saturated, or even in general, when do we, what exactly is the formulas that we expect in QCD? That's an interesting question.
Excuse me, but this comes from a fit to a power law, or
Yeah.
didn't they try to fit the power of a log?
Yeah, I think, but it doesn't. I thought that this. Okay, I don't know. My impression is also you can add log square plus log, and it also kind of works. But I don't think there is a reason to expect that the Froissart bound is saturated with current energies, and this is somehow this is also consistent with everything. So I don't know how at this point, maybe experts know better, but based on general grounds, I don't see a reason to try to fit the amplitude with the logs. It can be equally a power.
By the way, here, to what amplitude are you referring to? The scattering of
this one?
Yeah.
I think it's like universal fit, what works for many processes, but we say for proton. So yes, I will stop here, and the next time we will discuss. So this is a story of unitarity, and the next time we will discuss analyticity.
Don't clap.
Any questions from the students?
Because I'm over time, we can do it for the evening also. I'm sorry.
Okay. Yeah, so just unmute yourself now, or if you prefer to discuss it tonight.
Okay, let's.
Yeah, so let's postpone questions to tonight's discussion session.